Okay, and I'm Jeremy Holt, of course, local at the Nuclear Theory Group here at the University of Washington. And so today I'll basically be talking about some ongoing work where the goal is to look at nuclear few and many-body systems using lattice techniques. So first of all, what are the main motivations for doing traditional nuclear physics, say in discretized space? Well, I think there are two very strong incentives. So the first is that there are important nuclear 3 and 4-body forces, which are very often neglected in most nuclear structure and reaction calculations. And I think that working on the lattice can significantly simplify their implementation. And secondly, a longer-term goal is to establish a stronger dialogue between the lattice QCD community and low-energy nuclear physics. And I think by developing these lattice methods in the low-energy sector, one can start to have a more productive interplay between these two communities. So formally, these lattice methods are grounded in the so-called discrete variable representation basis. So in the second part of the talk, I'll describe the main, sort of the main features of this formalism, as well as some recent efforts we've done to construct chiral nuclear potentials that are consistent with different choices of your lattice parameters. And then finally, in the last part of the talk, I'll look at some initial applications to light nuclei and then also infinite neutron matter.
Jeremy,
yes?
Can I ask a question? I mean, you may be answering it later.
Yeah.
You can just say so. But I usually never thought of DVR type techniques as a lattice technique in the sense that the way I know it, you don't actually have to renormalize the interactions or anything like that, like one would usually do on a lattice. Is that something you're going to address?
I don't think I'll address that topic specifically. So what I mean just by lattice is that basically your bases are localized around discrete points in space. So I mean that's basically what I mean by doing physics on the lattice, so to speak. I mean you only need to look at your wave functions in most cases at discrete points. So.
But you would know it anywhere in between, right?
Yeah, there are interpolation. Yeah, exactly. There are nice interpolation techniques. I'll describe that a little bit later too, as well. Yeah. So of course we would like to understand nuclear many-body systems from QCD, but in most cases the best we can do is just construct a low-energy effective field theory of the relevant degrees of freedom. So namely the nucleon, the stable nucleons, as well as the lightest mesons, the pions. So on the one hand, this effective field theory takes advantage of the observed separation of energy scales in the light meson spectrum. And on the other hand, it incorporates dynamical constraints coming from the symmetries and the symmetry breaking pattern of QCD. So there are some open issues regarding the correct power counting, but the basic strategy, nevertheless, is just to construct order by order in powers of this light scale divided by the high scale, various contributions to nuclear forces and currents. So this has already been computed up to fourth power or fourth order in powers of Q over lambda in the case of nuclear 2, 3, and 4-body systems. So as far as the 2-body systems goes, you have sort of at short distances, you have unresolved dynamics, which are encoded in these contact terms, which you fit to NN scattering phase shifts. In the 3-body sector, you do have two short distance parts, which are and associated low energy constants, and these are typically fit to, say, the Tritown binding energy and lifetime. Now at N3LO, in the 3-body and 4-body force sector, you have quite a few additional contributions. So there are actually no new low energy constants, but they're very difficult to include in present day many-body methods. And the main reason is because it's very difficult to evaluate these, say, in a partial wave basis or a harmonic oscillator basis, which is actually what most people need, most researchers need, as a starting point for their calculations.
So why is that so difficult? Just because you need many terms, or?
So yeah, in the case of four-body forces, so if you have to evaluate this in a partial wave basis, I mean, I think that's extremely complicated.
So that's fine, but then the three-body, you sounded like three-body was also more difficult than the order three.
Yeah, it is. So I think what's holding them back is that here you actually can't derive all of the expressions analytically, so you have some remaining integrals that you have to do in addition to whatever additional integrals you have to perform when changing bases. So I think it's not sort of conceptually difficult, it's just taking a huge amount of time to actually do this on the computers. So.
I have a comment here. You may know that beside this partial wave decomposition calculation, we have also a three-dimensional representation that we avoid the partial wave representation, and we work directly with vector variable.
Oh yeah, Charlotte Elster, right?
Yeah,
Yeah,
exactly.
yeah, she's done some work.
Can we have this 3D representation of the color potential, especially for this term, that the evaluation of this element would be complicated for different partial wave?
So if in that case, it wouldn't be, I think, a problem in your case. So, right, so you don't have to actually do the full partial wave decomposition, is that correct? Or
we consider all of the partial wave, I mean, that
sort of.
So the problem would be the fitting the low energy coefficient to, I mean, the universal energy region, because here we are fitting to a specific channel the low energy coefficient, but in the 3D representation, we have the potential for, I mean, that independent of the range of the energy that we have, and for example, by solving the Blitzmann-Schwinger equation, at the end we can have the two-body matrix that we can project to any specific partial wave that we need.
Yeah.
So I was thinking that probably the representation of this, I mean, the terms in 3D representation.
Yeah, so wait, are you talking about just two-body forces or also three and
3 and 4 even.
as well? Okay, okay.
But can you do, I thought you could only do the three-body problem, two and three-body. Can you do four-body also with this non-partial wave expanded?
Yeah, we have done, I mean, that for two and three body interaction, and for four body, okay, for example, in the four body calculation, we have one term for the four body force that we need to consider in the formalism for the Federico-Bowski equations.
Okay, yeah, maybe it'd be interesting. Have you looked at
No.
these guys? Okay, maybe it would be.
This is just because of the question that they asked. We can discuss about it.
Yeah, maybe it'd be interesting to talk later. So yeah, but yeah, so I would say that most nuclear structure calculations are currently being done in an inconsistent way. So they'll typically use two-body forces at N3LO, and then only include many-body forces at N2LO. So of course this has some problems, and it's actually quite easy to see that if you don't include consistent forces, then you immediately violate, say, the Pauli principle. So if you just take this particular contribution to the two-body force at N3LO, of course these are constructed in free space, but in a nuclear medium you should have this intermediate nuclear propagator seeing the filled Fermi sea. But you actually only take into account these Pauli blocking effects if you include corresponding three-body forces at the same order. So if you just contract these two, this incoming and this outgoing line, then you exactly get like a Pauli blocked version of this diagram. So here you just write the in-medium nuclear propagator as the sum of this free space part plus this so-called medium insertion. But in addition to violating Pauli principle, often what you find is that there are significant cancellations among different diagrams at a given order. And so here what I show are the contributions to the energy per particle of symmetric nuclear matter and neutron matter, so just as a function of the density, including only a four-body force which has two intermediate state delta excitations. So what you see is that when you do all the contractions and calculate the Hartree-Fock contributions, you have various topologies. So in particular, the three-ring diagrams give a repulsion, say at nuclear matter saturation density, of about 5 to 10 MeV per particle. whereas these two-ring diagrams give a traction of just a little bit less. But nevertheless, individually they're quite large, but if you take them together, maybe you're still getting about 2 MeV per particle of repulsion coming in from these four-body forces, which are completely being neglected in calculations to date. So I think there's strong motivation to include these higher order 3 and 4-body forces, both for consistency as well as for getting the correct physics. Okay, so as I mentioned before, the main problem is having to do a partial wave decomposition of these forces, or evaluating them in a harmonic oscillator basis. So the chiral potentials are naturally represented in a plane wave basis. So one method, of course, that doesn't rely on evaluating the potential in some other basis is just to discretize, discretize coordinate space, and then you force your particles to lie on individual lattice sites. So then correspondingly in momentum space, you have a similar set of grid points where now the infrared and the ultraviolet cutoffs are associated with, say, the length, the total box size in coordinate space, as well as the lattice spacing in the case of the UV cutoff. So this would be nice. It would, if you do your calculations at a plane wave basis, it should be easier to evaluate these higher body forces. And this gives you a finite set of single particle states with which to work with. So really the question, though, is how to choose values of the box size and the lattice spacing so that you have converged results. This depends, of course, on sort of the underlying nuclear potential that you're using. And so what we wanted to do is develop consistent nuclear potentials with different types of lattices. But essentially all we're doing is just sort of a calculation in a finite model space. And what's been found over the last basically decade or so is that if you evolve essentially any realistic nuclear potential down to a resolution scale of about 1.5 Fermi lattice spacing, then what you find are very good convergence properties both in perturbation theory as well as calculations in finite model spaces as you just increase the number of basis states you're working with. However, the bad features or the undesirable features associated with these renormalization group methods is that you can have induced many-body forces and currents which may or may not be well under control. And also the analytical form of the potential is lost, which can be a problem for some methods. So what we wanted to do, instead of using these renormalization group techniques, rather just lower the cutoff scale in the chiral potential and refit the low energy constants, so in the 2 and 3 body sectors. Yeah.
Can you elaborate on give an example where it's a disadvantage not to have it analytically anymore? Just take too long to evaluate that numerically if you need to interpolate, or is there any more fundamental?
There would be a more fundamental problem. So it will kind of come up later. So when you're using, if you're doing Lanczos method, say in momentum space, you want to have some sparse matrix. But in Lanczos, if you only have the potential in, say a partial wave basis, then you have overlaps among, I guess, a lot of the different momentum states. So maybe in that case, it's a little inconvenient. So we found it's much more convenient to use.
Eliminate exactly that by pushing into the diagonal? I mean, that should just decouple.
Oh yeah, but you can only push it so far to the diagonal, right, before you're generating many body forces. Yeah, so actually the techniques that I'll be using later there, it's particularly convenient to have the potential in an analytical form. But not all methods really have a problem with that, though.
So you're going to say more later about in which coordinates you discretize and whether you have, say, equal spacing everywhere? Or?
Yeah, so this talk I'll basically just be confining the discussion to equal lattice points, even though there are DVR bases where you have unequal lattice spacing, etc. Yeah, but.
And it's in the Cartesian coordinates.
Yeah, right. So just have a direct product of 3 Cartesian coordinates. But there are alternatives, which sort of we're looking at the moment. Yeah, yeah. Any other questions? Or? Okay, yeah. So what we wanted to do is, yeah. So basically most chiral. Well, basically most people are using this Entman-Mach-Lite 500 MeV cutoff potential, but then also with Mach-Lite and other collaborators, we constructed these potentials at some lower cutoff scales, where in particular we expect this guy to be very well converged, both in perturbation theory as well as in finite model space calculations. So here we see fits to various nucleon-nucleon phase shifts. At N3LO, the two-body contact interactions only allow us to fit up to D waves. So the only freedom we have in these peripheral partial waves is to refit these CI coefficients associated with the 2 pion exchange 3-body forces and 2-body forces at N2LO. So that's what we did in the peripheral partial waves, just refit the CI. And then in these lower partial waves, we refit the NN contact terms.
How different are they if you compare them with the ones you get from pi n scattering?
Oh, I think they're basically all within the error band. So the CI, so really C3 has the largest effect on these partial waves, and it ranges from, yeah, basically negative 3.0 to, yeah, negative 3.4, just varying the cutoff here.
Okay, so you're keeping the consistency.
Yeah, they're consistent with pi n scattering, I think, yeah.
Doesn't that mean, strictly speaking, that if you had gone back and varied the underlying CIs with whatever potential you started with and got an error band for your results from that, then you don't actually gain anything by refitting things to get more precision, if you consider the error from the CIs?
Well, with the errors from the CI, you're still at a particular resolution scale. So you are gaining something because the underlying cutoff scale of the potential is different. Yeah. But you're right, if you did just take this guy and varied these CIs in this way, then you should be within the same, yeah, error band. But yeah, I think we are doing more than that. Okay, so yeah, we do get very good agreement with phase shifts up to about 200 MeV. I think this sort of raises the question, though. How high in energy does one need to fit phase shifts? Because this 500 MeV potential fits pretty well up to about 350 MeV. But as you lower the cutoff, you get basically poorer and poorer agreement with phase shifts. But nevertheless, I think we'll see that this still gives us pretty reasonable physics, this scale. Okay, so I just want to show here the perturbative properties of these potentials. So the 500 MeV cutoff potential, you can see the convergence properties are not bad. So this is first order, second order, third order perturbative calculation of the neutron matter equation of state. But nevertheless, you expect to have significant, maybe fourth order contributions. However, for the N3LO 414 MeV cutoff potential, you see extremely good perturbative behavior, right? So first order, second order, and then third order is already on top of second order, essentially. So this is, one could have maybe already predicted this based on these RG calculations, but explicitly this is what we find. And yeah, it's important to note that in the case of neutron matter, the only 3-body force that contributes is this 2 pion exchange contribution that includes the CI coefficients. So then if one looks at not the perturbative properties, but rather the scale dependence of the neutron matter equation of state, then what you find is that with 2-body forces only, there's a lot of scale dependence. But sort of amazingly, there's very little scale dependence when you include these consistent 3-body forces. So that's sort of a nice feature that we observed. Of course, we wanted to extend these to symmetric nuclear matter, but that requires, in addition, the 3 nucleon contact forces proportional to CD and CE low energy constants. So we started a new collaboration with Laura Marcucci She's able to do some hyperspherical harmonic calculations of Triton and helium-3. And so what we did is so there are these two new three-body forces at N2LO that come into play in symmetric nuclear matter. And if you just fit to the Triton and helium-3 binding energies, you can't really distinguish CD and CE, but rather just some linear combination of them. And this shows a set of consistency curves. So basically any value of CD and CE along this curve will reproduce the Triton and helium-3 binding energy. But you can't distinguish them further. For that, the best way is to look at the Triton lifetime. So in this case, what comes in is this CD contribution to the two-body nuclear axial current, and as well as the C3 and C4 coefficients in, say, what was the 2-pion exchange three-body force diagram. But nevertheless, this is going to contribute to the Triton lifetime. And here this shows the calculations that Laura did for these different cutoff potentials and really fixing CD very precisely just to the Triton lifetime. So this is the theoretical divided by the experimental. There's some error band, but nevertheless, this can pin down very accurately the value of CD, which was first suggested by these guys a couple years ago, and then also carried out by Deuteron and collaborators. Okay, so with these values of CD and CE, we can now do some systematic calculations of symmetric nuclear matter, just to study the convergence properties and also just how well they describe the physics. So here we did a consistent third-order calculation. I don't know, for those of you who appreciate this kind of thing, we included for the first time this third-order particle hole diagram, which is pretty challenging. But yeah, here basically we see the convergence properties of this low cutoff potential. So here's the nuclear matter equation of state, the empirical saturation point shown down here, this pink dot. And this is the first, second, and third order contributions. So again, the perturbative features look pretty good, but the scale dependence isn't quite as good as what we saw in the case of neutron matter. So in particular, this 500 MeV cutoff potential, which probably isn't converged in the first place, it's significantly underbound. It gives nuclear matter that's underbound compared to experiment and then also these lower cutoff potentials. So in any case, I think the take-home message is that these low cutoff potentials, they're well converged in many-body perturbation theory, seem to give pretty good description of nuclear matter. So we'd want to use them now in our calculations of, say, light nuclei, neutron matter. Yeah.
Sorry to bother you again with another question. Have you compared what you get when you just take the 500 MeV and use some VLOK method to get it down to the same cutoff as your 440 without any fitting?
So that's difficult, right? Because you should also consistently evolve three-body forces. So what people have done in the past is they'll do, say, a VLOK decimation down to this cutoff scale, and then they refit the CD and the CE parameters. So that's sort of one strategy, but I think in the end it's not really consistent. And in fact, I think there have been some more recent calculations by Kai that shows that such an approach doesn't really well capture the full RG evolution. Just refitting CD and CE.
Yeah, but in that kind of plot, where would the curve lie?
Oh yeah, it's actually pretty good. So it's, I would say it's pretty comparable to these guys. Yeah, they did calculations for a range, and I think their band more or less went through this. Yeah, but they found similar things, like the high cutoff potential was underbound, and then as you do the RG evolution, it goes down and sort of goes through the saturation point. Yeah.
So what would you have? Would be your claim what you have to do to reproduce this point, or one should not reproduce it eventually?
So why these guys don't quite work, or What?
Well,
or-
I mean, so you say that many-body perturbation theory is converged with those forces. So
Yeah.
I think the conclusion from that is if you do fourth order, this won't get you any closer.
Exactly.
Then maybe it's four-body forces, or what's
Yeah.
your...
Yeah, no, I think the take-home message is that probably this additional discrepancy is due to missing contributions in the force. So we already saw that four-body force maybe give a couple, 1 or 2 MeV of repulsion. So the three-body forces, yeah, who knows, one has to actually calculate them. But yeah, I think that's what the missing physics is. But it's not, I think the calculations are pretty well converged as we saw.
And the potential you use, so this is consistent N2LO. Did I understand that correctly?
No. So this is actually inconsistent. So we're still, actually all of the calculations I'll show right now are still inconsistent. But nevertheless, we're working on the N3LO 3 and 4 body forces. Sorry, maybe that actually wasn't quite clear here, since I motivated it from a totally different,
So can you say explicitly in which way inconsistent? Because I
Yes.
remember your consistent.
Yeah, so I said
introduction.
that, yeah, so we're still in this group of people who are doing inconsistent calculations. But that's the motivation, is that we want to get away from that.
But do you have a consistent N2LO number?
Oh, a consistent N2LO number. I don't, but there have been calculations, and they seem to have overbound nuclear matter. So this was done with the this N2LO pounders, optimized chiral potential. So they did that consistently. Although I'm actually not sure how they refit the CD and the CE parameters, whether they use this Tritown calculation or just fit to, say, the alpha binding energy. But yeah, nevertheless, they did one, and it was
So then,
overbound.
Then, I don't know, these Pauli blocking effects that you mentioned, they might also contribute to that.
Yeah, exactly. So yeah, that's a good point. Maybe what I was saying was misleading, but these are still inconsistent calculations. Okay, so any other calculations, questions before I go on to the next section?
I wonder if the scale dependence would also go away if you did it consistently even at N2L. So here, how you see the scale dependence?
Yes. Well, if you take a potential and really consistently evolve with RG the 2, 3 body, 4 body forces, then it has to be scale. That calculation has to be scale independent, because you're not changing the physics at all. Yeah. But I think in that case, the induced many-body forces may or may not be well under control. One has to study that. Okay, so now that we have these potentials, which seem to have pretty good perturbative behavior, let's see what actually happens in say an exact calculation within finite model space. So so there's this discrete variable representation, which I think is a sort of a generalized lattice technique. So it's one of the most widely used methods for discretizing the Schrödinger equation. And its main virtues are that it preserves the locality of operators, at least approximately. So in the case of the potential energy, for instance, it's very easy to evaluate these local operators. Also, in many cases, at least for appropriate potentials and boundary conditions, you have rapid, in fact, exponential convergence of the calculation as you extrapolate in the IR and the UV. And also, direct product DVRs typically lead to sparse matrix representations of the Hamiltonian in multidimensional problems, and easily coupled to iterative techniques such as Lanczos. So in particular, this is what we'll be using to solve, say, the Deuteron, Tritown, and alpha particles later. Okay, so the DVR, as we'll see, it's a quasi-local in coordinate space, but it's discrete. And so that's why I've been calling this basically a lattice technique. So formally, what you do is you just start with any finite set of energy eigenstates that define a projection operator. So for instance, maybe you look at the set of plane waves below a certain cutoff in momentum space. So this isn't difficult. You can basically use any spectral basis, but then what's the tricky part is that you have to find a consistent set of grid points such that these projected delta functions satisfy a non-trivial requirement, namely that when you project these coordinate eigenfunctions onto your spectral basis, then the resulting functions are orthonormal, or at least up to this constant n alpha. So as we'll see, this basically follows immediately that basis functions, so these delta alpha, then have nodes at all other lattice points, and they're only localized about discrete points in coordinate space. And also they have this nice quasi-locality feature that if you evaluate some local operator in these two basis states, then you approximately just get the potential at that point times this normalization constant. So yeah, we're basically just going to be using the plane wave basis, but in principle you can construct more complicated DVR sets that don't correspond to, say, equal lattice spacing in coordinate space. Yeah.
What controls this approximate identity there? How can you scale the error down by just choosing one mesh point?
Yeah, exactly, yeah.
Because it's just numerical
Mm-hmm,
noise.
yeah, exactly. Yep, so you just want to take sort of finer lattice spacing.
So what do you mean by non-trivial requirements?
Well, if you take some, if you just take some set of let's just take some spectral basis, it's actually difficult to find a set of lattice points that satisfy this. That's what I mean.
Requirement on the lattice points? Or?
Yes. So this, this maybe looks like a trivial requirement, but it's very difficult to satisfy or to find a set of lattice points that consistently satisfy this for all lattice points.
By requirement on the lattice point, you mean how the lattice looks like?
Yeah, just where the lattice points are.
Okay.
So
You're saying that you just do
in the case of plane waves, yeah, you have just you can easily prove that the consistent set of lattice points are just equally spaced, where the spacing depends on this momentum cutoff. But if you were to take, say, like a Bessel function basis or something, then it's a little bit more complicated to find lattice points. But that actually has been done. But this is basically all that goes into the formalism. And then if you can find a set of lattice points that's associated with your desired spectral basis, then that's perfect. Okay, so yeah, we're basically just going to be working in momentum space. So we look at really momenta below a cutoff Kc. And then in that case, you can show that these projected delta functions are just the sinc functions, which, as you can see, are localized about discrete points in coordinate space, and they have nodes at all of the other points in the basis. So actually you get these, if you had a continuous set of momentum space matrix elements, then yeah, you get actually an infinite number of points in coordinate space whose lattice spacing is just associated with this upper momentum cutoff. But if you look at discrete points here, then that corresponds to fixing coordinate space within a box. Okay, so, but if it's continuous, in principle, you'd have infinitely many lattice points in coordinate space. No, it doesn't. No, it doesn't satisfy. So I'll actually discuss a periodic DVR basis in just a second. So yeah, this would be maybe associated with Dirichlet boundary conditions if you wanted to cut it off. But yeah, I'll discuss the periodic DVR basis in just a second. And then this is just what happens if you, say, double the lattice spacing. So obviously, for a given basis function, all you do is just have additional nodes at half the lattice spacing. So what's particularly convenient about the DVR basis is that functional interpolation is very simple. So if you have some arbitrary function and you want to interpolate it at an arbitrary point off a lattice site, then all you do is have to evaluate the potential at each of the individual lattice sites and then multiply by the appropriate DVR basis function associated with that site. So here I just show what happens. So here's actually, if you have a periodic function, then instead of regular sinc functions, you have these periodic sinc functions. Maybe you can see here. And yeah, so if one only has this particular function at these discrete points in coordinate space, then what I did here is just used this prescription to interpolate across all space. And this works very well, actually. So regarding the convergence properties, both in the IR and the UV, basically what you have to do, well, you can use phase space arguments to understand how convergence is reached. So if you look at something like this Morse oscillator potential, and then you have some semi-classical orbits shown here in the momentum and coordinate space, then if you want to reproduce, say, the physics of these lowest 1, 2, 3, say about 4 states, then you can do that with a harmonic oscillator basis as long as the harmonic oscillator basis covers those 4 semi-classical orbits. And one can show that once you enclose a particular state that you want, then as you include more and more basis states beyond that, then you reach exponential convergence. But in this calculation, if you only included these 10 harmonic oscillator basis states, then maybe you could get this guy to about 10% precision. You still do need to go beyond in order to get the exponential convergence. So anyway, the DVR basis states that I've been talking about, they basically partition your phase space into these strips where a particular DVR function is localized around a particular point in coordinate space, and then in momentum space, it's set by your cutoff scale. So this is what we would want to completely overlap our semi-classical orbits that we're interested in. So here's a case, just a simple calculation of the harmonic oscillator using this DVR basis, these plane wave DVR bases. And this is just some high order harmonic oscillator wave function. And what we do is we show here the convergence of the lowest, say, n states for a given choice of lattice spacing and maximum momentum cutoff. Okay, so here you can see the lattice spacing, and it's associated with this maximum in momentum space. So what you find is that with this particular grid, you have the lowest 5 eigenvalues are extremely well reproduced up to machine precision. So as you can see, you do have to go beyond the phase space associated with the semi-classical orbit really to get machine precision. But nevertheless, you can get about 24 eigenstates that are within about 10% of their exact value. And those are shown where they've just completely been enclosed by our sort of our DVR basis phase space coverage. So as one goes to finer mesh points associated with P and then also larger box sizes, one can better reproduce these harmonic oscillator eigenstates. So there we get 8 and 32. And then finally for this, say, DVR basis, one gets 14 excellent and about 40 good eigenstates. So this just exhibits the convergence associated with this phase space coverage arguments. Okay, so I just wanted to quickly talk about sort of similar methods that are being used in in traditional shell model calculations. So we heard some talks about this the last couple of weeks. So in a harmonic oscillator basis, if you want to study a nucleus, then you have to do calculations up to some maximum up to some maximum n associated with the harmonic oscillator wave functions. And typically what one associates with the UV cutoff scale is basically the energy associated with your highest included harmonic oscillator wave functions. So this is, I think, sort of well motivated, but there was always some discussion regarding the correct choice or the correct understanding of the infrared convergence of harmonic oscillator calculations. So some people took it to be like the sort of the spacing associated with this energy difference. And then in some more recent calculations, they associated the infrared cutoff scale with the inverse of the sort of the spatial extent of the highest coordinate space wave function, right? So these harmonic oscillators, these harmonic oscillator wave functions, they decrease like Gaussian, with a Gaussian function outside of the potential, whereas nuclear wave functions should only decay exponentially. So it's sort of always a challenge to get the correct IR scaling behavior. So that's one of the main, I think, advantages of this DVR approach, is that the IR and infrared scaling and convergence is a lot better under control. So there is still some ongoing discussion in the literature about the correct choice of how to really scale these traditional shell model calculations in the IR and the UV.
So in your DVR calculation, is the infrared and ultraviolet also coupled, or is it independent?
Independent.
So that's like in a box.
Exactly, yeah.
And the idea that you have with this is you do your extrapolation to large box size. You just do this numerically, or are you thinking of doing some effective theory calculation that captures this?
Right now we're just doing it numerically. So whether we can derive some functional form that gives us fewer fit parameters or whatever, I think we're going to look into that in the future. But right now, I'll show like in a slide or two the convergence properties, say, of the Deuteron and how we extrapolate. Yeah. I think just to save a little bit of time. So yeah, one can play around with simple functions, study the IR and the UV convergence. I think I won't go into much detail here since these aren't really realistic forces, just giving you some idea of the exponential convergence both in the IR and the UV. But yeah, so here's a first calculation of the Deuteron. Actually, unfortunately, we haven't incorporated chiral nuclear potentials yet. So first I just looked at the argon V8 prime potential and the convergence properties of the Deuteron binding energy. So both as you lower the, as you increase the resolution in coordinate space, and then also the box size. So the argon potential actually requires a pretty fine resolution scale in coordinate space. So here, if you fix the box size to some, 20 Fermi box, then the convergence as you increase the number of lattice points. So basically, you're fairly well converged at a lattice spacing of about 0.5 Fermi. But what I said previously is that these chiral potentials should be well converged at about 1.5 Fermi, or maybe even a coarser resolution scale. So that can significantly help with the computational times as compared to these hard argon potentials. So then if we fix the lattice spacing at 0.5 Fermi and then just increase the box size, then we see this really nice exponential convergence. However, to get a purely converged result, one has to go way out, right? One has to have this huge box of 30 Fermi. So I didn't put the units here, but this is in Fermi.
Jeremy, I may have missed it. Are you using periodic boundary conditions?
Yeah, these are using periodic boundary conditions.
Can you motivate that? I mean, I would expect when they have a Deuteron, and there's nothing periodic in the Deuteron, right? All it does is the wave function is going to fall off somehow.
Yeah.
And if I have repeated boxes,
Yeah.
then I have the problem of having energy contributions from
Yeah,
this,
yeah, exactly.
What's
So,
the advantage of making the problem wrong?
oh, what's the advantage? So you would want to impose Dirichlet boundary conditions, for instance?
And then you don't have any image problems, right? Because you have the second system sitting next to you that induces another force.
Yeah, exactly. But I mean, you also have errors associated with that as well, right? So you'd also have finite box size corrections there. Since you're forcing the potential to be zero at the boundaries.
We also have image because
I'm sorry?
usually boundary condition.
I mean, you also have finite volume corrections to that as well, right? Either way.
Your box big enough, and you also know that there's no physics happening, so you just use non-equal spacing, and you space your points going out on a,
Yeah.
grid.
Okay. I mean, I don't right now see the advantage. So we didn't implement Dirichlet boundary conditions in these calculations yet. So my view is that one has, yeah, of course, if you go out to large enough boxes, I think with both sets of boundary conditions, obviously you get the same results. But in both cases, you get corrections. Right? Oh, do you have a comment?
Actually, for periodic boundary conditions, these finite volume exploration formulas are known, so you can actually use it as a tool to analytically extrapolate.
Yeah, exactly.
Also,
That's
the
what we'll.
degree of the Deuteron in that case, you can actually treat that independently and extrapolate exactly for these kind of boundary conditions.
Yeah, so that's
So
what
it's more
I'll.
like a tool than a problem, I would claim.
But are there similar? So yeah, I know that's true with these periodic boundary conditions. I just didn't know if the same is true for if the analytical form of the finite volume corrections with Dirichlet boundary conditions are well known. I don't know if that's true or not, but I don't know.
Could do that, but the point is for periodic boundary conditions, they
It's
are
well
known,
known.
so why not just use that?
Yeah. So that's actually what we did. So here is the extrapolation. So there's this, so here are the volume corrections associated with periodic boundary conditions. So if you just do the calculation in the box, you get the infinite energy limit plus this finite volume correction. And in a number of papers, it was shown that the form of this is just an exponential in minus L over some length scale associated with your bound state. And so what happens, I actually have data point at a box size of 4 and 6, but they're way down here, so I didn't put them on the graph. But if one extrapolates from those 3 points up to here, then you actually get within about 20% of the Deuteron binding energy, even though you're well over 200% corrections in the absolute value of the energy. And then if you extrapolate from this point, you get within 10%, and this point you're already within 2%. So I think that's a nice feature. You don't actually have to do these calculations, right, till they're converged. You have these nice extrapolation functional
Is A a
forms.
fit parameter in your case?
Yeah.
So if you really were in a cubic box with periodic boundary conditions, A is predicted, but then you don't have to fit that. And sort of my question is, can you think of your problem like that? Is it just a box that is implicit in your basis, or do you really put the system?
I
like,
think
in a finite
so.
box?
So I did, I mean, I looked at some of these papers, so I didn't really, so what is this associated with? What kind of analytical form do you
It's
have?
not in those papers. There
Okay.
are different papers where it depends on the binding momentum, and then there are just pure numbers factors. So
Okay, yeah, maybe you can.
You should talk to
It's
Sebastian.
the ANC of the Deuteron square, the asymptotic normalization of the wave function and some prefactor, I think 3 pi or something like that.
Okay, yeah, we should talk about it later.
Is it inversely proportional to EO0? Is A inversely proportional to this parameter EO0? Is lattice?
Or associated with EL, or what, or how?
I mean, you have
What
this
does it-
equivalence EO0. From dimensional analysis, I would expect A is inversely proportional.
I think L0 is also the binding momentum, right? And the ANC is given by the binding momentum, so they depend on the same quantity. But maybe that's something for the discussion session, because that
Okay, yeah, but we can discuss that later, yeah. Okay. And then finally, there were some initial calculations done with quote-unquote Tritown and alpha particles. So one didn't take into account the fermionic nature of nucleons in this calculation, so you just treated these 3 and 4 particle systems as distinguishable spinless particles with these different potentials. So a Gaussian and then this Purcell-Teller potentials. And then basically they just computed, well, as in our other calculations, we just computed the lowest energy eigenstates from Lanczos. And they used a number of different lattice spacings as well as associated with these cutoff scales, and then varied the box size. So this corresponds to increasing box sizes. So previously we were using periodic boundary conditions, which give you overbound systems just due to like tunneling effects. But these upper bounds are what happens when you impose Dirichlet boundary conditions, like Dirta was mentioning. And so what you can see is that, of course, as you go to large enough volumes, then everything is well converged. But for something like the alpha particle, clearly you see the need to do some kind of extrapolation because the number of basis elements required in this calculation is actually quite large, and one can't get converged results at this order. So these calculations were actually done just on a laptop computer with something like 16 gigabytes of RAM. But yeah, we want to, of course, the goal now is to calculate alphas and tritons using realistic 2 and 3 body forces, but within the same framework.
What does this PT and 2G mean?
The 2G, these are just different potentials. So the 2G it's a sum of 2 Gaussian potentials, and then this PT is some Purcell-Teller potential. I don't remember the exact form actually of it in this case, but
And all I'm supposed to see here is that this converges.
basically, and that Triton and alpha calculations are feasible, say on a standard laptop with a lot of memory, maybe. So just sort of a proof of principle, what kinds of systems can be calculated. So this is really treating the full, I mean, here you have 9 coordinates. You don't do any kind of spherical decomposition or anything. So you really just have a huge number of.
In front, and say 2.
Yeah, these are just, so one takes, so you have V2G, which is just a fixed potential, and then they just multiplied by some constant. Yeah, so it's just a constant multiplying the function, yeah. But in all cases, these are just the ground state energies. Yeah, so to get the, yeah.
So could you remind me, so this DVR basis has advantage that you can fit the basis to your physics, and then you take only a small number of, or this phase-space argument which you mentioned. So you're doing it on a lattice which is not, it's not optimized.
Yeah, you could.
Problem. So is your motivation because of this decomposition of the potential?
Well, so my motivation is to choose. So I want to continue doing calculations in this particular basis because I think it'll be convenient for including these N3LO 3 and 4 body forces. So one could choose a DVR basis that takes into account spherical symmetry, but that's going to, I think, sort of spoil this Knight's feature that I mentioned in the beginning. So that's sort of my motivation, is to study these higher order forces.
That you would have a lot of, so this basis is not optimized.
I would say it's not optimized just because, yeah, you have a huge number of basis states if you don't incorporate spherical symmetry or anything like that. So you're really just solving a 9-dimensional Schrodinger equation or whatever. Yeah.
So if you would optimize, then it would be difficult to extract.
It would be difficult to implement these 3 and 4 body forces, I think. So that's sort of my motivation, yeah. Mm-hmm. So this is basically, any other questions at this point? So I did have one extra section, but I think I won't have time.
When you at least have 10 more minutes, right? I talked for 10 minutes at the beginning of your talk.
Okay. So then let me quickly go to the last topic, which So previously we were looking at few body systems, but one can also use these lattice methods to study, say, infinite neutron matter, which was done in collaboration with Gabriel and Oral in particular, also Sergey. So we're all involved in this project. So basically what we wanted to do is look at infinite neutron matter. Of course, in practice, we have to choose just a finite set of, or I mean just a finite number of neutrons. But what we do is, to get the ground state energy, we just take some arbitrary starting wave function and evolve it in imaginary time. And then as long as you have a non-zero overlap with your exact ground state wave function, this evolution in imaginary time filters out the correct ground state. So we're going to use the auxiliary field technique just to get rid of these 4 fermion interactions, and instead nucleons interact directly with this background stochastic field, and therefore indirectly with each other. So this results in some complicated multidimensional integration, which you can then evaluate using Monte Carlo methods. So we just break up the imaginary time slices into small steps, and yeah, then just propagate. And so one has in coordinate space and then also in imaginary time space this background field, which you use sort of standard metropolis sampling to sort of optimize. So yeah, this sort of a similar procedure is currently being used, in particular by Dean Lee and collaborators. But since chiral nuclear forces exhibit the sign problem, they're nevertheless restricted to rather light systems. So our maybe rather ambitious goal is to simulate several hundred neutrons using potentials that don't exhibit the sign problem. So basically, if you take some attractive interaction, that's one of the main, so an attractive and also spin-independent potential. So this doesn't exhibit the sign problem. So if you just have a sum of Yukawa potentials, so here we took as our evolution Hamiltonian, so the kinetic energy plus the 1 pion exchange Yukawa potential, which is attractive, plus sort of a fictitious sigma and omega. So the sigma is attractive and the omega we take to be repulsive. But as long as the sum is always negative, then we can do Monte Carlo simulations without a sign problem. And this allows you to study up to several hundred nucleons on the lattice. So what we do is we fit these 4 different parameters associated with this attractive and repulsive Yukawa interactions. So we constrain them by fits to phase shifts, as well as the perturbative equation of state, which we can calculate. And then we get some density dependence in our evolution Hamiltonian, but we can nevertheless evolve to the correct ground state of this evolution potential. So here I show what happens for the lowest density case in our calculation. So this is 38 neutrons on a lattice with 1.5 Fermi spacing, which corresponds to this 414 MeV cutoff potential we derived in the beginning of the talk. So what we do is we just evaluate our trial wave function using this evolution Hamiltonian, and then we evaluate the chiral Hamiltonian at N3LO in this evolved wave function. And one can show that that's basically a first order perturbative contribution to the equation of state, this prescription. So we have nice convergence in imaginary time. So here are some occupation probabilities that we calculated. And in particular, this, as you might expect, since the evolution potential gets weaker and weaker as we go to higher and higher densities to sort of account for repulsive 3-body forces, this depletion at at low momenta becomes weaker and weaker as our evolution potential becomes correspondingly weaker.
Is this something like the momentum distribution?
Yeah, exactly. The momentum distribution. Mm-hmm. And yeah, here we see this sort of exponential fall off. Yeah.
I didn't say anything.
Oh, okay. Was it a 5-minute or you're just?
No, I was just spreading my fingers.
Okay. Okay, this is the final slide though with actual results. So here are our calculations for the equation of state of neutron matter. So here, yeah, unfortunately, we're still doing an inconsistent calculation. Namely, this is the two-body force at N3LO, and it's basically consistent with other auxiliary field quantum Monte Carlo calculations done at N2LO using two-body forces only. This is Alex Gazerlis, Achim Schwenk, Evgeny Eppelbaum, their collaborators. So they derived a set of nuclear potentials at different resolution scales, and their band is shown, I don't know if you can see it by just these dotted lines. So their scale dependence is in here, and we're basically right on top of their, for some reason we're like right on top of their, one of their potentials. But we did the calculation at N3LO, so we have some additional repulsive contributions, as can be seen here in the decomposition. And moreover, we included the leading order three-body force. But of course, the next step is to include the N3LO 3 and 4-body forces. But nevertheless, we are a little bit ahead of the game in respect to those two calculations. Also, Rogero et al., who recently also studied an N2LO two-body force calculation of the equation of state using different Monte Carlo methods. This is what they obtained using two-body forces only. So I would say we're all relatively consistent in the two-body sector, or in the two-nucleon force sector, but then we also have these additional three-body forces, which give, as you can see, sizable repulsion, even at these, even below nuclear matter saturation density. Okay, so yeah, I think I'll just leave this up here. I'm basically out of time, but I hope I've convinced you that these lattice approaches are well motivated. We still haven't achieved what I wanted to in the beginning, namely consistent 2 and 3 body forces, but that's in the works, and I think it's certainly manageable. So yeah, in the future we'll extend these calculations of light nuclei. We can certainly do Triton and alpha, and then we also want to explore more of these Monte Carlo methods. So thank you.